Okay. I'll begin then. Thank you for the invitation and good morning. So I'm going to tell you a little bit about some of the ongoing research that's in laser plasma acceleration that's going on in Berkeley lab right now. I think you've been having this workshop for a couple weeks now, so I think you're all well aware of what laser plasma accelerators are and what they can do, and they're great interest because of the large fields they can produce and their ability to produce a compact source of energetic E-beams. So I'm going to tell you a little bit about some of the experimental results in our lab here in Berkeley. It's called the Bella Lab, which stands for the Berkeley Lab Laser Accelerator. And I'll tell you about some of our results on GeV beams, multi-GeV beams, and centimeter scale plasmas. And then I'm going to talk a little bit about controlled injection techniques, which is a topic of great interest to us here. You know, these are methods to sort of improve the beam quality and stability. And it all has to do with the trapping physics. So I'll talk a little bit about the trapping physics and some of the methods we're employing, in particular using density gradients and ionization. And then some ideas we have on how to produce very low emittance beams using triggered injection. And then I want to switch to tell you a little bit about applications. You know, what applications are of interest with these compact accelerators. So I want to tell you a little bit about how to use these LPAs to drive a free electron laser. And then I want to tell you a little bit about hydrogen physics applications of LPAs. And this is really the application that we're mainly funded to do here in Berkeley Lab. And I'll conclude by telling you some of our preliminary experimental results on staging of laser plasma accelerators. This is a recent result, and discuss our plans for going forward. Now, this is a sort of a typical laser plasma accelerator setup. You have a high sapphire laser with a few joules, a few tens of femtoseconds. It's focused on target. We use hydrogen discharge capillaries mainly. We use these to form a plasma channel to help guide the laser pulse. And so in this particular experiment I'm showing here on this view graph, the plasma density was about a few 10 to the 18 per cubic centimeter, and the plasma length was a few centimeters, and we were able to produce GeV beams with tens of picocoulombs of charge, 2% energy spread, and about a millirad divergence. So, you know, in these experiments, electrons are self-trapped from the background plasma, and they're accelerated over the 3 centimeters, and the beam exits the plasma and is measured on a magnetic spectrometer with these sorts of characteristics. So this is a typical sort of GeV class experiment. You all know this quite well. The characteristic size of the plasma wave is the so-called cold wave breaking field, which scales like the square root of n, the density in the plasma. So for these sort of 10 to the 18 per cubic centimeter plasma densities, we expect gradients of order 100 gigavolt per meter. So this is several orders of magnitude larger than conventional RF accelerators. The bunch duration is also quite short, and I'll show some evidence for this later in my talk. It's a fraction of the plasma wavelength. So with these beam charges of a few tens of picocoulombs and these short bunches of a few femtoseconds, this implies peak currents 1 to 10 kiloamps. And so that's sort of a number that's very interesting for applications, especially the free electron laser application. All right, so what's in this experiment I showed you, what's limiting the energy gain? Well, the energy gain is this characteristic accelerating field times some interaction length, you know, in general. And so usually the most severe limit to the interaction is the diffraction of the laser. So the laser will diffract on a scale length of order the Rayleigh range. This is typically the most severe limit, but this can be controlled. So you can either control this by tailoring the transverse distribution of your plasma, so that's forming a plasma channel, and that's what we do often in the lab. Or you could use relativistic guiding or quantum mode of self-channeling to also guide the laser pulse. However, it should be mentioned that these plasma channels have some advantages, because if you want to rely on relativistic self-guiding, it pushes you to higher laser powers and higher plasma densities. And as I'll discuss in some detail, you really want to go to lower plasma densities to get higher energy gains. And in this regime, the self-channeling and self-guiding is not as effective. Okay, once you've guided your laser pulse, sort of the next limit is dephasing. This is well known. You have some beam moving at some velocity, and your wake has some phase velocity. Your plasma wave, and it's approximately the laser group velocity. So there's some difference in these velocities, and the beam, the relativistic beam will typically slip forward with respect to the plasma wave, and so that'll limit the energy gain. This plasma wave phase velocity is only approximately the laser group velocity. In this sort of nonlinear regime that people typically operate, evolution of the laser will be a dominant factor in determining this phase velocity. And in principle, this could be controlled by tailoring your plasma. And I'll discuss a little bit about controlling the phase velocity by tailoring your plasma later in the talk. But of course, the ultimate limit is the laser energy depletion. Your laser is depositing energy into the plasma, forming the plasma wave, which then accelerates a beam. The rate of laser energy deposition is sort of proportional to the plasma density, the -3/2. You can work that out. Here's some recent papers on that topic. So this sort of, the higher the density you are, the quicker you deplete your laser energy, and your shorter your depletion length. Okay, so you can use these sort of plasma density scalings to try to understand what's going on in these experiments. As I just described, your acceleration interaction length scales like this density to the -3/2. Your characteristics accelerating gradient scales to the density, square root of density. So you'd expect the total energy gain, the product of these two, to scale like 1/density. And so here I'm plotting E-beam energy gain versus plasma density for a collection of experiments. And I apologize if I didn't include your favorite experiment, but the general trend is clear. If you want to go to higher energy, you need to go to lower plasma density. And this also is one of the reasons that you sort of are forced into a staging approach if you want to go to very high energies, and I'll discuss that later in the talk. You can't continually going down in density because your accelerating gradient is continually reducing as well. And once the accelerating gradient gets low enough that it's competitive with conventional technology, it's no longer interesting. So you're sort of limited to some density, and at which point you need to start staging these laser plasma accelerators. Okay, so for each dense operating density, there are some laser requirements. Basically, you're at the volume your laser occupies has to be the plasma wavelength cubed or proportional to the plasma wavelength cubed, for a resonant interaction. The pulse duration needs to be proportional to the plasma wavelength, also to resonantly drive your plasma wave. So these two conditions imply as you go down in density, you need more laser energy and more laser power. So for that initial experiment I showed you, I think on my third slide, we were producing 1 GeV. We were using 3 × 10⁻¹8 per cubic centimeter plasma. We were accelerating over about a centimeter of distance using a couple joules of laser energy, and it was about a 100 terawatt laser system. So if you imagine you want to increase the beam energy to 4 GeV, you'd expect to reduce the density by a factor of 4, increase your acceleration length by a factor of 8, your laser energy required goes up by a factor of 8, and your laser power would have to increase by a factor of 4. So that's what these scalings would tell you if you use the same physics to generate your E-beam. So this is sort of the experiment we did. So at Berkeley Lab, we have a petawatt class laser system. It's called the Bella Laser Facility, Berkeley Lab Laser Accelerator. It can produce up to about 42 joules in 40 femtoseconds, and it's at 1 hertz. So this is I believe this is the highest rep-rated petawatt laser system in the world. And this was commissioned 3-4 years ago. And so here's sort of a picture of the system. These are the pump lasers. This is the compressor. There's an OAP, off-axis paraboloid, about a 10-meter-ish focal length. Here's the target chamber. And inside the target chamber, we have our plasma source, which is our discharge capillary. And then there's diagnostics downstream for the E-beam. So this is exactly the experiment we did. We created a 9-centimeter hydrogen discharge capillary plasma. That's our target. The on-axis density was about 7 times 10 to the 17 per cubic centimeter. We used 16 joules of the Bella laser energy. And this indeed produced a 4 GeV E-beam with a few percent energy spread, submilliarad divergence, and about 10 picocoulombs. So that's what you'd expect it. Higher energies could be achieved by, as the scaling indicated, by going to lower plasma densities. However, you're going to need longer plasma channels, and it's a bit of a technical challenge to create these channels over that distance. And in addition, by going to lower plasma density, you can no longer rely on self-trapping. So that's sort of the trapping physics we used here, and you'll have to use some triggered injection. But the Bella laser system should have enough energy to go to 10 GeV, and that's sort of our future goal. All right, so as I mentioned, those 2 experiments I showed you use self-injection or self-trapping to produce the electron beam from the background plasma. And in general, this requires high laser intensity. So this is sort of the normalized vector potential of the laser. And the intensity you need really depends on the phase velocity, the plasma temperature, a number of factors. But in general, requires also high plasma density. And this high plasma density slows the plasma wave phase velocity and allows there to be trapping. And so this is just a quick simulation of the trapping process to give you an idea of what's going on. This is the plasma density. The laser is sitting here, moving left to right and producing an E-beam. Now, this self-trapping can have some issues, and one is sort of a continuous, uncontrolled injection, and that can result in large energy spreads. So that's sort of shown over here. This is a snapshot in time of the plasma density and the trapped beam in the self-trapping regime. And what's happening is electrons are sweeping back along the sheath of this bubble or ion cavity and getting trapped in the back here and then accelerating forward. So the particles at the head of the beam have high energy and the particles behind have lower energy. And so this is the longitudinal phase space, and you get this sort of characteristic energy chirp distribution. So that's quite generic from this self-trapping method. And what you'd like to do ideally is to do some controlled triggered injection where you can turn on and turn off the injection in a very controlled way, and this will improve the stability as well as reducing shot-to-shot fluctuations. Okay, so let me tell you a little bit about maybe the trapping physics, and before I describe how you might do that. So one can study this self-injection process in detail, and it's typically done using thick modeling. And we did a pretty detailed study of this trapping process. Here I'm showing again that picture of the electron density. This is the plasma density, and a bubble being formed by a laser. This is at a particular laser intensity, so normalized vector potential of 3.5, and a particular phase velocity. So this is the ratio of the laser frequency to plasma frequency, it's 20. And in this case, I plotted a few orbits, but there's no trapping. And then you can imagine increasing your laser intensity. So it's really the same condition. I've gone from 3.5 to 4. So the bubble size has grown a little bit. Same sort of density conditions, and now you can have trapped particles. So that indicates there's some threshold to this trapping process. I mentioned the phase velocity is very critical. It's not just the intensity of your laser. And that's sort of shown in this picture. So here is the outline or the intensity contour of the laser. It's forming this bubble with some border. And these are different electron trajectories for different phase velocities of your plasma wave. So at high phase velocity, 60 or 40, the electron is not trapped. This is an electron with the same initial condition. And then as you lower the phase velocity, so this is gamma phase of now 20 or 10, the electrons then become trapped. So again, there's some threshold in phase velocity for the particles to become trapped. And so you can sort of plot in parameter space the normalized laser field strength versus this wake phase velocity, which is proportional to 1 over the square root of density. And you can see, let's see, this is showing the black dots here means there's no injection, and the color dots means there's some injected charge. So for high phase velocity, low amplitudes, there's no injection. For slow phase wake phase velocities, large laser field strengths, then you get a lot of injection, and then there's some threshold you can numerically determine. So what, if you want to operate at high density with low density to get a large energy gain, then you typically run into a problem of injection. It's more difficult to inject using self-injection. But you can use a few techniques to get around that. And one is to control the phase velocity with density gradient. So this is an old idea that was originally proposed by Sergei Bulanov almost 20 years ago. So the basic idea is you have some plasma wave with some phase here. Maybe it's periodic. And if you compute the phase velocity, you see it's a function of the group velocity of your laser pulse and the evolution of this plasma wave number. So if the plasma wave number is evolving as the laser is propagating, this can reduce the phase velocity. So here's the driver velocity. It's basically 1 moving near C. It's changing, rather minor changes, but this term can have a dramatic effect. And this can be controlled either using density variations, or it can be controlled using laser evolution. So if you're in the nonlinear regime and your laser is evolving through self-focusing, for example, then the plasma wavelength will also evolve. The larger the intensity of the laser, the larger the nonlinear plasma wavelength, and that will affect the phase velocity. So here's something you might imagine doing. You can consider a density distribution like this with maybe a hump and then a flat region. And then you can plot the phase velocity corresponding to this corresponding to the wake excited in this density profile. And that's sort of shown in this blue curve. And there's also the effect of the laser focusing on top of that, which also can change the phase velocity through the evolving plasma wavelength. But in general, as the laser goes up and drives a wake on this rising density gradient, you have a superluminal phase velocity. When it's dipping down, you have a low phase velocity. And then here, because of some laser evolution, it again dips up to superluminal. And what you'd expect is that right here, you'd have a very localized region of trapping. Because the phase velocity is only low in this region, and then you can imagine post-accelerating downstream. So a very localized trapped beam. And so we explored this concept at LBNL. We did an experiment trying to utilize this injection mechanism. So here I'm showing sort of the experimental configuration we came up with. It's a high-density gas jet, which is a few millimeters in length, and it's embedded into one of these discharge capillaries that's a few centimeters of length. And so this sort of configuration will give you exactly this sort of density profile, where the gas jet here now would serve as an injector, and then this capillary will then post-accelerate the injected beam. And then we did demonstrate, this is just the injector, and this is the injector plus capillary. And depending on the laser focus, which determines the laser evolution parameters, you can determine the location of the trapping and the energy gain in your beam. So that's one technique. Now, one of the simplest and most effective techniques to trigger injection is to use ionization injection. And this is a very common technique, as you're probably aware, in the community. So again, you want a larger energy gain is achieved at lower plasma densities, as I've discussed. But this lower density means a higher plasma wave phase velocity, and it's more difficult to self-inject. So one way to get around that is to use ionization injection. And the basic idea here is you have some gas, maybe hydrogen and helium, and then you dope it with a little bit of a high Z gas, maybe adding some nitrogen, and then you ionize an electron from the inner shell near the peak of the laser, and this traps and produces and lowers the trapping threshold. So how does this work? So here's sort of a basic schematic of why that works. So here I'm showing the laser profile, the intensity profile. And if you imagine an electron being ionized or born at the foot of this laser, it slips back and it starts gaining momentum in the backward direction. As it keeps on slipping back, it moves into this accelerating region, and then it starts gaining energy in the forward direction. But by the time it's reached the back of the bubble, it hasn't gained enough energy to be trapped, and it slips out the back. And that's sort of shown in this longitudinal phase space plot, where I'm having, this is the co-moving phase of the plasma wave, and this is the longitudinal momentum. Now, if you imagine ionizing later at a higher intensity, then the electron gets less of a momentum gain moving in the back going direction. And it ends up having a higher forward going momentum after it's slipped back to the back of the bubble, or this plasma wave bucket. And then if it gets ionized at the peak, it can gain a sufficient forward going momentum to be trapped. And that's sort of shown in this red curve here. It's now on a trapped electron orbit. So that's the basic concept. And one can calculate the trapping threshold for this case. And if you imagine an electron ionized and slipping sort of along the axis, so sort of a 1D calculation, but along the axis, the center of the bubble, you can calculate the injection threshold. And that's sort of shown here. Again, this is the normalized laser intensity, and this is the wake phase velocity. This was that self-trapping condition that was calculated. And here, this curve, this bottom curve, is now the threshold for ionization injection for electrons being born at the peak of the laser. So what does this tell you? A single pulse ionization requires lower laser intensity. Normalized vector potential is about A of 2 or greater. It's pretty weakly dependent on the plasma density. And this is what allows you to go to much lower densities with this technique and get higher energy gains. Now, one potential problem is that since you've made trapping so easy, it's easy to get continuous injection. That will result in larger energy spreads. Maybe you might imagine having a finite region over which you have a mixed gas to sort of localize the injection. There's another issue with this idea, is that electrons that are ionized at the peak of the laser exit the laser with some residual momentum due to the quiver in the laser. So this technique tends to give you larger transverse emittance beams, which can be a problem. So what you'd really like to do, if you could do it, is you'd like to separate the Wake excitation process and the ionization injection process. So this is a concept we're exploring we call two-color ionization injection, and it relies on two lasers of different wavelengths to really provide this separation and functionality. So the idea is to start a large plasma wave, you need a large quantum motive force. So you need a large intensity or A squared. And to ionize, you really need, it's determined by the peak of the laser field, so the electric field, so you need a large electric field, right? So the idea is here you can use a long wavelength laser pulse with a small electric field to excite your Wakefield. And the idea is here that since the electric field is low because of the long wavelength, it won't fully ionize your gas. So there'll be some trapped bound electrons remaining. And then you come with a short wavelength pulse, delayed with respect to the Wakefield driving pulse. And this will then ionize some inner shell of electron, which will then proceed to be trapped. And the advantage here is now you're ionizing your electron at a small laser vector potential, so that the residual transverse momentum exiting the laser pulse is small, and you can produce very low emittance beams this way. So that's the basic concept. Here is a 3D PIX simulation of that idea. This is using the code WARP, written by Jean-Luc Bay. Here is the main drive beam, long wavelength. Here is the short wavelength injection laser pulse. So this beam drives the wake, but doesn't fully ionize the plasma. The injection laser pulse does some additional ionizing and traps a high-quality electron beam. And you can work out sort of what emittances you expect based on the spot size of your injection beam, the amplitude, the wavelength, the gas you're using. And for these parameters, you can produce normalized emittances of tens of nanometers. So this is an order of magnitude lower than you can produce with self-trapping or from conventional photo injectors in that case. So this is an interesting idea to get ultra-low emittance beams. All right, so I want to switch a little bit to applications now, in the time remaining I have. So you can generate GeV beams with kiloamp currents, and in principle, you can get excellent beam quality. What would you want to use these for? So, of course, you can use an LPA generated E-beam for any application that uses an E-beam. But the most interesting applications take advantage of the unique features of laser plasma accelerators, and primarily the high gradient. So if there's a premium on compactness, then that's a very interesting application. These beams intrinsically produce have femtosecond time structure. So applications that take advantage of the short bunch structure are interesting. And of course, you have this natural laser particle beam synchronization. So if that's required for your experiment, LPA is a very, very interesting application for that. So here I've listed a few ideas for radiation generation. You, of course, can use the short bunch structure to generate high field Territz radiation. So if the bunch is of order a micron length, then you can use coherent transition or fraction radiation of the short bunches. So that's very interesting. Let's see. So for some nuclear detection applications, you require portable sources of gamma rays, right? And so those can be compactly generated by scattering a laser pulse scattering a laser pulse off a LPA beam. And this is a sort of a diagram from some work done at University of Nebraska to use Thomson scattering to generate MeV photons after an LPA beam. I'm sure you've heard about betatron radiation applications, and I want to spend just a couple of moments talking about the free-electron laser application, because this has generated a lot of interest worldwide, perhaps the most interest in terms of applications. And the basic idea is, you have these large kilometer scale X-ray FPLs. And so the dream is, well, let's replace that with sort of a meter scale device based on laser plasma accelerators. And a lot of people are working on this topic. So here's, again, sort of the generic beam characteristics produced from an LPA. You sort of have hundreds of MeV beams, few percent energy spread, tens of picocoulombs of charge, few femtosecond duration. Typically, you can have good submicron emittance. This is really encouraging. These are nice greater than kiloamp beams. So that's nice for the FPL application. Sort of the problem, if you will, is that the energy spread is large. It's about an order of magnitude larger than the FPL bandwidth. And so this sort of prevents lasing of the beam in an undulator. So usually it's said that the FEL, or the beam quality of the LPA beam, is too poor for the FEL application. Now, the proper metric for beam quality, of course, is the 6T beam brightness. So this is the number of particles over the 6T phase space volume. And if you look at this number and compare an LPA beam, so this is typical parameters, maybe submicron emittance, half a GeV, a few percent energy spread, so kiloamp currents, you find that very comparable to state-of-the-art photocathode sources. And so what that's telling you is that the beam quality of these experimentally produced beams is actually good enough to drive the FEL. It's just not properly distributed for this application. So you can imagine realizing this application with some phase space manipulation or redistribution of your electrons in your beam. And there's lots of ideas you can look at, potentially emittance exchange or collimation or some phase space redistribution. And so there's two ideas I want to briefly mention are longitudinal decompression and then transverse dispersion. And these are both paths to lasing in an FEL with an LPA beam. So the basic idea is quite simple. You have this very short bunch, but its energy spread is too large. What matters for the FEL application is really the slice energy spread, not the projected energy spread. So one idea is you can take this beam and put it through a chicane. So this is just 4 dipole magnets. And what will happen is the high energy particles will take a short path and the low energy particles will take a long path. And this will stretch out your beam in time. So the high energy particles will be ahead and the low energy particles will be behind. And now you can see, as I've drawn here, that the slice energy spread, the energy spread at one particular slice of the beam or time slice, is now quite small. And so you can imagine doing this until this slice energy spread is less than the FEL bandwidth, which is typically written as rho. Now, this also, of course, will reduce your peak current, and that will affect the FEL instability. And there's sort of a trade-off between these two effects, these two competing effects, but you can optimize this. And so here I'm plotting the normalized FEL gain length versus this normalized energy spread, so relative energy spread normalized to this FEL bandwidth. So typically when this normalized energy spread gets of order 1, then you get this sort of growth in gain length, and this suppresses the instability. But now if you do this optimal decompression technique, you can tolerate much higher energy spreads. And in fact, the growth of the gain length only scales like the square root of this parameter instead of quadratically. So that's quite favorable. Now, that's a longitudinal arrangement. You can also do a technique by dispersing the beam transversely. And so the idea here is that you have this FEL resonant condition. And so if you imagine sorting your beam so that at each energy is located at a different transverse position. So the energy of the beam is some function of its transverse position. And then you imagine put it into a canted pole undulator, such that the magnetic field in the undulator is also a function of the transverse position. So for the low energy electrons, you give it small gamma, you give it a large, a small magnetic field, such that, and then for the high energy guys, you you have them experience a large magnetic field, such that you can, if you do it right, you can satisfy this resonant condition for every electron in this beam. And so there's some condition on the dispersion of your beam and the cant of your undulators, such that your resonant condition is satisfied for all your electrons. And again, you can analyze this and optimize this, and this really allows you to, the FEL to accept much higher energy spreads than it would otherwise. All right, so you can compare these two ideas. So what I'm showing now is an laser plasma accelerator-driven FEL in the water window at 4 nanometer using electron beam phase space manipulation techniques. So this is sort of realistic but optimistic laser plasma accelerator parameters, sort of 1 GeV, 10 kiloamp, 1% energy spread, 5 femtoseconds, and 50 picocoulombs. And so what I'm showing here is the average power along the length of the undulator for 3 cases. The blue is if you do nothing with your LPA beam. The red is if you do this dispersion plus a transverse gradient undulator, and this black here is if you just stretch your beam, so just decompress it. And what it shows is that using either of these phase-space manipulation techniques, you can get saturation. So that's the saturation of this exponential growth of the power over the 5 meters. Of course, if you stretch your beam longitudinally, you're going to lose longitudinal coherence, and that's sort of what's shown here. The dispersed beam, the red one here, is longitudinally coherent, whereas the long decompressed beam has many spikes in the spectrum. But in the dispersed beam, you'll lose transverse coherence, and that's what's shown here. If you stretch your beam inversely, you'll end up with multiple modes, and then you'll lose some transverse coherence. So those are 2 ideas on how to use existing laser plasma accelerator, I would say experimentally demonstrated parameters to operate a free electron laser. So at LBNL, we have a program to demonstrate FEL lasing, and we are taking the simpler approach to start with, which is beam decompression. So if you're using this beam decompression, FEL lasing requires a sufficient peak current after you've stretched the bunch such that the slice energy spread is less than the FEL bandwidth. So what does that mean? That means you require a sufficient spectral charge density following the laser plasma accelerators. So you need a sufficient, it doesn't matter if you have a large energy spread, in other words, you just need a sufficient picocoulomb per MeV, say, such that when you stretch the beam, you'll have enough current to lase. And so this is an example of a beam we've generated in the laboratory using a discharge capillary. And it has a 10% energy spread, which is much too large to put in the FEL directly, but its spectral charge density, picocoulomb per MeV, that's the measurement here, is about 2, which is what is required to get lasing. So what we have in this setup is we have this LPA capillary. We're operating at 250 MeV. The FEL instability is stronger at lower energy, so it's a little easier to do a demonstration experiment at lower energy. We focus the beam using plasma lenses, and I'll discuss that in a moment, how that works. Then we use a chicane, electromagnetic chicane, to stretch the beam. And then with this spectral charge density, we'll have enough current after the beam is stretched to laze in our undulator. We currently have the Visa undulator, which is about 2 centimeter. We have about 220 periods, which corresponds to about 4 meters. And we expect to be able to saturate with this demonstrated beam at 67 nanometers over the 4 meters. And so this is a beamline that's undergoing commissioning right now, and we expect to start taking data about a year from now. All right, so now I want to switch gears to high energy physics applications of laser plasma accelerators. So this is sort of the long-term and definitely the most challenging application envisioned for this accelerator technology. And so I think you're all aware that conventional accelerators have reached have sort of saturated, and that's due to a limit on the gradient due to material breakdown. So the gradients are limited to of order 100 megavolts per meter. And so this, I have showing a plot here from an old paper, but still relevant today, of collision energy. These are high energy physics machines versus year of completion. The blue here is lepton machines, so E plus E minus colliders, and the red is hadron machines. Of course, right now the LHC is in operation with a circumference of 27 kilometers. And people are imagining a future linear collider, now called the International Limit Collider, ILC, operating at about 500 GeV, center of mass. And here's a little diagram of sort of what that's envisioned to look like. And it's hard to read, but this length here is about 31 kilometers. So it's quite large. And it's really determined by the achievable gradient. So, for example, 50 megavolts per meter implies you're going to need 20 kilometers to get a TeV. So the next future Lepton Collider, a TeV or multi-TeV scale, has to increase this accelerating gradient. And then it should be noted, of course, the facility cost scales with the facility size, and most of the cost, at least for the ILC design, is in the main Linacs. So you really want to, you're going to need a new technology if you want to go forward. So, one could say that you need to do a TeV or multi-TeV will require at least an order of magnitude increase in the accelerating gradient. If you go away from metal structures, you can imagine dielectric structures, which could get you to a gigavolt per meter. Plasmas, of course, which are already broken down, can do of order 10 gigavolt per meter or more. And of course, you can drive these with either beam drivers or laser drivers. I've only been talking about laser drivers in this talk, but I'm sure you've discussed beam drivers also at this workshop. And there's been a lot of progress in LPAs in the last 20 years. And so here on this plot, I'm plotting, again, a collection of experiments, and I'm sorry if I missed your favorite one. But here's the year demonstrated, and on this axis now is electron beam energy. And you see there's a nice trend of progress due mainly to better understanding of the LPA physics and the development of laser technology. Okay, so if you really dream of a Lepton Collider, what's required from the high energy physics standpoint is collisions with electrons and positrons. So sort of one potential advantage that laser drivers have over beam drivers per se is you have a path to accelerating positrons by operating in what we call the quasi-linear regime, such that the intensities are only weakly relativistic. So here I'm showing a case with an intensity of about 10 to the 18 watts per centimeter squared. The top figure is showing the accelerating field generated. The middle figure is the plasma density. The bottom figure is the focusing field. And, and there's regions of electron acceleration and positron acceleration. This is, the nice thing here is it's relatively symmetric. There's regions of electron focusing and positron focusing. And then you can imagine injecting your beam at the proper phase for both electron acceleration and positron acceleration. So an important question to consider is what is the operational plasma density? So in this talk I've been discussing a lot about plasma density scalings. What density would you like to operate such a machine, right? So one optimization you might do is to minimize the size of the linac. So this is maximizing your average gradient or geometric gradient. So your average gradient is going to be determined by your peak field in your plasma. So here I'm showing two stages, LPA plasma stages, and coupling a fresh laser to drive the second stage. And so your average gradient is really going to be determined by your coupling distance as well as your peak gradient and plasma length. So another potential advantage of lasers is that you can compactly couple in lasers using plasma mirror technology. So if you imagine using conventional laser optics, you'd require many Rayleigh ranges to couple this in. But if you imagine using plasma mirrors, you can couple in a very compact distance. So here I'm plotting the length of for example, TV stage LPA linac. That's the length here, and this is versus density for a few stage coupling distances. And what you see is that for very high densities, you have high gradient, many stages, and the total, but your average gradient is going to be low because of the coupling physics between stages. If you go to low density, you want to use one or a few stages, then your distance is your total linac distance is going to be determined by plasma stage length. And then there's some optimal to minimize the LPA linac, and it's a border between 10 to 16 and 10 to 18 per cubic centimeter. So that's sort of the density region you want to look in. Now, the other consideration besides the average gradient would be the average power required. This is an important consideration. So if you look at the charge in a bunch, the charge in a bunch basically scales as the laser energy you put in over the energy gain in a single stage. And if you recall the density scalings for these two quantities, that goes like 1 over the square root of density. Now, if you imagine there's some fixed luminosity goal, this collider needs some luminosity to get some event rate. The luminosity scales as the rep rate times the punch density squared. So for fixed luminosity, the rep rate of your laser has to go like proportional to the density. And so your average power, which would be the rep rate times the laser energy, then scales like the square root of density. And this implies going to lower plasma density reduces your average power requirements. So this is some, example TV collider for some parameters. And here it's showing the power required in megawatts versus plasma density. And so this really pushes you to lower density. However, the reason you're getting away with this is that you're increasing your charge per bunch by going to lower and lower density. But the problem with this is there's a limit to the charge per bunch. And this is due to beam Stirling. So what is beam Stirling? When you have the electron and positron beam colliding, at the interaction point, at the IP, the fields from one beam will scatter off the charged particles in the colliding beam, and this will produce photons. So this is basically synchrotron irradiation of one beam in the fields of the colliding beam. And so the number of photons produced per electron has this scaling. So the more charge you have in your bunch, the more photons you're producing. And the effect of this has is not just background, but it also you're actually radiating away energy in your beam. And it can be so severe that you radiate 100% of your energy in your beam. This number of photons per electron also scales like the bunch length to 1/3. So the fact that the laser plasma accelerators produce short bunches is an advantage. But overall, it has this density of the -1/2 scaling, which I'm plotting right here. So this is the average beams per lung photons versus density. And so, for example, CLIC, which is a Lepton Collider proposed by CERN, is planning to use about 2 beams per lung photons per electron. 3 is too many. 3 is basically you're radiating all your laser energy away, or your beam energy away during the interaction point. So you want to be sort of in this regime, and this sort of points you again to plasma densities of order 10 to the 17 per cubic centimeter. So you can, put together a straw man concept based on these scalings. If you want to minimize your construction costs and your operational costs, this indicates you want to operate about at 10 to the 17 per cubic centimeter. You want to be in sort of this quasi-linear wake regime so you can do positrons as well as electron beams. And so for sort of these densities of these intensities, this means you're using about a few tens of joules of laser energy per stage to get a few GeV per stage in less than a meter. So that's sort of what you want to design. And that's sort of, the thrust of our program here at Berkeley Lab. Right now we're doing multi-GeV experiments. So these are single stage experiments. And of course you have to stage many of these together. So we're doing staging experiments as well. And so now I would like to tell you a little bit about our recent staging experiments, and then I'll just conclude. Oh, I should really point out that, all these laser plasma physics problems are very hard, but actually the hardest or the biggest challenge to dreaming of some collider like this is the laser technology development. I mean, these require very high rep rate lasers, tens of kilohertz, with average powers of tens of kilowatts and extremely high efficiency. And so these lasers that you need to do this don't exist today. All right, so let me tell you about some of the work we've done on staging laser plasma accelerators. So the key here is that each stage is independently powered by a separate laser. So here I'm showing the experimental layout. So the first stage here, we want to sort of establish a stable injector stage. This is what we call stage 1. So we have about 1.5 joules laser when we focus onto a gas jet, which is about 5 times 10 to the 18 per cubic centimeter plasma. It's helium doped with a little nitrogen. And we use ionization injection to get a very stable, reproducible E-beam. And that's sort of shown here, where we can really have a stable beam that lasts over thousands of shots. And this is showing the mean energy and the charge of the beam. This is a waterfall plot of the same data, produced over 1,000 shots. It actually lasts for 1,000. So this is a very stable beam, a way to produce a nice beam. And that's critical because we're going to do some scanning experiments here. So after the beam comes out of the jet, what's critical is that you need to refocus it on the second stage. So refocusing the beam is not trivial, and what we developed is what we call an active plasma lens to do this. So the idea here is that the beam enters a gas-filled capillary, and when the beam enters the capillary, we strike a discharge, so we flow a current through the capillary. And this current produces an azimutomagnetic field with a field gradient proportional to the current you're driving, and over the cap radius squared. And so this is sort of a solenoidal field that can give you a symmetric focusing of the E-beam. And it can, so we here in this cap was 1.5 centimeters, and you can really produce up to thousands of Tesla per meter. So you can very compactly focus the beam symmetrically using this active plasma lens. And so we focus the beam at the entrance of a second laser plasma accelerator stage. Now the second laser pulse is coupled in using a tape-based plasma mirror. So we're actually using a VHS tape here. So it compactly couples in the second laser pulse, which in this case is about 500 millijoules. There is no observable mode or pointing deterioration using this tape, and you get about 80% throughput in the laser energy. So we use this tape to very compactly focus the second laser pulse, which is of course synchronized with the first, onto a discharge capillary. And so this second laser is about half a joule, an intensity about 1.4 times 10 to the 18 watts per centimeter squared. So it's operating in a sort of, quasi-linear regime, and where we expect no self-trapping. And then we measure the E-beam distribution using a magnetic dipole, and we scan the delay between these two lasers. And so that's sort of what's shown here. Here's the reference beam again, this reference beam from just the gas jet. And then here in these four plots are the energy spectra from the measured on the dipole magnet at different time delays. And what you see is some delays you get an energy gain, some delays you get an energy loss, gain, loss, gain, loss. And so you're sort of sampling the linear plasma wave by varying the delay between the laser pulses. Okay, and so here's some data showing that essentially. This is the experimental data here on the left. So this is the electron spectra as a function of delay between the first laser, which is the E-beam, and laser, the second laser. Here we've subtracted off the background spectra, or the spectra from the first laser plasma accelerator. And so what you see is there's periodic regions of acceleration. There's approximately 100 MeV energy gain in the second LPA stage. What it tells you is that indeed we're operating in this quasi-linear regime, which is consistent with the laser plasma parameters. So intensity is about 10 to the 18 watts per centimeter squared in the second laser pulse. You see multiple accelerating buckets. Here it's, I think, eight buckets are shown. The modulation here between these accelerating regions is about 80 femtoseconds. That corresponds to 24 micron plasma wavelength, and that's consistent with 2 10 to the 18 per cubic centimeter is what we expect in the plasma capillary. And what this also tells you is that we also have a bunch length that's shorter, coming off the first stage, that's shorter than a quarter of a plasma wavelength, so less than 6 microns. And we did a lot of detailed start-to-end simulation here using the Inferno PIC code. This was developed by Carlo Benedetti, and you get fairly nice agreement with the measurements. All right, so that's what we did, and that was published last year. Where do we want to go from here? That was essentially showing about 100 MeV beam in the first stage, and then we boosted the energy about 100 MeV in the second stage. So what we want to do in the future is we want to use the Bella laser system to do multi-GeV in the first stage and then boost multi-GeV in the second stage. So the layout might look something like this. You take the Bella beam, you split it in two. 15 joules hits the first stage. There's some injector, probably a region of ionization injection, could be down ramp, and then about a 30 centimeter cap to accelerate the beam to about 5 GeV. Then again, we'd use this plasma lens technology. So the beam coming out of the first stage is diverging. You capture it in this plasma lens and focus it. down to the entrance of a second stage. And then in the second stage, you'd couple in again with the tape-based plasma mirror, 15 joules of the Bella laser, and you'd post-accelerate from 5 GeV to about 9 or 10 GeV. And here I'm just showing several different delays. This is sort of the expected timing jitter, showing that this is quite robust with respect to this timing jitter. And this is showing the electron distribution after the injector. This is all modeling, of course, after the first LPA, and then what we expect after the second stage. So that's the what we're working towards at Berkeley Lab. And then I think I just want to used up all my time. I just want to conclude very quickly. I showed you 4 GeV beams in 9 centimeters using the LPA at Bella. Okay, we believe we can go to 10 GeV. We expect to do that in less than a meter of interaction, and that should happen in the next few years. What we're working on now is the channeling technology to get plasma channels at low density over the long interaction region to get the 10 GeV. I showed that the 6C brightness is comparable to conventional sources. Of course, you can do better than conventional sources if you're clever about your controlled injection. I talked about an idea to use laser pulses of different colors to produce very cold beams of order 10 nanometer emittances. There are, of course, many possible applications for the LPAs. I spent a lot of time talking about achieving FEL lasing using demonstrated LPA beams. This uses phase manipulation, and we're commissioning a beam line to try to do decompression of the beam for FEL lasing at Berkeley Lab. There are many other applications, of course. The collider application, this is what we're mainly funded to do. It has, it's a long-term, very challenging application, but key to this is staging. And so we've done some preliminary staging work at 100 MeV, accelerating another 100 MeV, and we're planning to move forward on multi-GeV plus multi-GeV staging experiments. Of course, if you want to do this, you need to also develop the laser technology. And my last comment is that, of course, the laser technology is rapidly advancing. 1 petawatt, 1 hertz laser systems are available today, like the Bella laser system. 10 petawatt, 1 hertz systems are under construction, will be available in the next couple of years. 1 joule, 1 kilohertz systems are also being envisioned, and I expect those will also be available in the next few years. So let me just end there, and I want to thank all of my colleagues at the Bella Center who contributed to this work. I'm happy to take any questions you have.
Thank you, Carl. Any questions? Yeah.
Carl, I got 2 questions. One is regarding the FEL applications. It appears to me that when you use chicane, obviously you are chirping the beam, chirping the electron beam. Can we actually find a way to start with a chirped electron bunch so that your delta E over E per unit time is quite small? So that's the first question. The second one is more practical.
Yeah.
When you go to higher rate lasers, obviously I don't know if you've done the staging at 1 hertz, but if you go to, let's say, 5 or 10 hertz, do you have a viable method for plasma mirrors? Because you'll run out of kilometers of tape in that rate.
Right. Okay, so the first question is, yes, you could imagine producing, by controlling the laser plasma interaction, producing a chirp beam in the laser plasma accelerator. But so the question really is, what is a slice of the beam? So in the FEL interaction, the slice is really the slippage between the electron beam and the radiation pulse. So and that's called a coherence length. or cooperation length. So this sort of defines your slice. And so for these sort of wavelength regimes that people tend to look at, so very soft X-ray or XUV FBLs, this cooperation length is quite long, and in fact, it can be a micron. So it can be the entire E-beam. So effectively, even if it's chirped, the entire E-beam is effectively one slice for the FBL. If you go to very hard X-rays, this cooperation length is reduced, and maybe you can imagine using a few micron chirped beam in that case. So for the second question, yeah, the station experiments I showed were at 1 Hertz. Our idea is to use the tape-based plasma mirror. Of course, you use up a lot of tape quickly. Right now, we don't have a better solution than that. So we're gonna stick for now. We're gonna stick with a tape-based plasma mirror. Yeah.
Yeah. We know that the making plasma channels at low density, especially for a long distance, is going to be a problem.
Yeah.
So are you looking for other methods of guiding, for example, using a dielectric capillary, which would be a completely independent, you would be decoupling plasma physics in a sense if you use...
Yeah.
So are you looking into those possibilities?
Yeah, great question. So I mentioned, we want to go to 10 GeV, and you may ask, how are you going to do it? Because it's very, very difficult to make these channels. So the idea we are looking at right now is the discharge alone won't create a channel deep enough to guide the laser. So we need to sort of dig out a deeper channel. So right now we're using another laser pulse. We call it a heater laser pulse. So this laser pulse would come after the discharge, but before the main pulse. And it would use inverse Bremsstrahlung to heat a filament in the long channel to dig it out more than the discharge can do alone. And we think adding this laser heater to dig out a deeper channel at low density will get us the parameters we want to get to. Now, if that doesn't work, you'll have to go to something else. And your idea of using a dielectric structure is a good one. Essentially it'd be a near hollow channel, maybe. Of course, the problem with that is doing it at rep rate. The plasma channel created in the discharge capillary also protects the capillary from the laser intensity, so it can survive thousands of shots. If you don't have that plasma channel, then you quickly damage sort of the walls of your structure. So when you're thinking about other ideas, it's tough to come up with concepts that are also compatible with the Hertz rep rate.
Hi. Thanks very much for very interesting talk. And with great clarity, you have explained various issues related to laser plasma accelerator. But I have a question on this use of petawatt laser for high energy electron acceleration. As I understand, for the 4 GeV beam, you have fired it maybe around 200 or 300 terawatt power only. So have you been able to fire shots at more power so that have you done further experiments with higher power on the target?
Yeah, we've fired the full laser energy on the 9 centimeter cap. So this would be the 40 joules. I mean, the problem is, at that density, you just dephase before you can get more energy gain. So you really got to fire the full energy, the petawatt, and at the same time you have to go to lower plasma density. Now the problem is then it makes self-guiding a lot more challenging when you're going to this lower plasma density. And so you really need to rely on some structured guiding, some channel. So just increasing the power alone isn't going to get you there unless you lower the density, and it's still not going to get you there because then it's going to be tough to guide at those low densities.
Okay. Another question on this use of plasma mirrors in your staged accelerator that you are using for injecting the second beam. You are using some tape target to reflect the beam and focusing into the second stage. So what was the size on the tape target of the beam, and how do you ensure this wave front and other issues for getting a good focus of the second beam?
I don't think I have the number on the top of my head. Let me see if I may have written that down. Yeah, you need to interact the beam at the target with sufficient intensity such that it, of course, ionizes the tape, creates a plasma, which then reflects the laser pulse. But you don't want it too intense that you have some coupling, where you'll lose energy through coupling between the laser and the plasma. So I believe it's typically around intensities of 10 to the 17 watts per centimeter squared they use to create the plasma and then reflect the pulse. Let's see. I don't have the spot size. So whatever that would correspond to. Let's see. The laser spot is in this case was 18 micron at focus, and it's order of magnitude less intensity. So then it would be about 3-4 times larger spot than that. So maybe of order 100 micron.
Okay. Okay. Thank you.
Sure. Oh, I'm having trouble hearing. I apologize. It's not coming through.
Hello?
Yeah. Now, yeah.
The energy spread in the beam seems to be 10% or more and seems to get worse with staging. Are there any tricks to improve that?
Yeah, exactly. Good observation. So if you look back, we produce in this gas jet, we produce a relatively large energy spread beam. And so the plasma lens is chromatic in the sense that different energies are focused differently. So this active plasma lens was set up to focus, I believe, between 75 MeV and 120 MeV. And that tends to spread out the beam at the second stage. So you're covering a large region of the bucket. And then that, of course, increases the energy spread. So if you go to, this is sort of part of the concept of our future experiments, is to create a beam with a lower relative energy spread, less than 10%. And then now reduce the chromatic effects in the cap lens and keep the beam, within a fraction of a plasma bucket in the second stage. So the problem with this experiment is that our injector, had too large of an energy spread. As you can see here, this is almost, I believe it was 30%. Yeah, definitely larger than 10%. So the way to get around that is to avoid chromatic focusing the lens by having a lower energy spread in the first stage.
A short question. In the FEL case, could you comment on the time structure of the outcoming FEL pulse? Because many FELs have a rather poor time profile. Would this be much better, which is what we may expect?
Right. So, So for this case, for example, the time structure of the radiation pulse will be that of the electron beam, roughly. So for this case, I'm showing it was a 5 femtosecond beam, and we decompressed it by a factor of 10. So it would be a 50 femtoseconds soft X-ray pulse, and it would be chirped in energy or wavelength, and that's what you sort of see here, because it'd be chirped in energy. Is that clear? Yeah.
The short-to-short variations, which a SASE
variations, right? Okay. Well, I mean, this is relying on SASE, self-amplified spontaneous emission. So you'd have, the usual shot-to-shot fluctuations based on a SASE FEL. Unless you're going to seed it, it's going to be, the number of longitudinal temporal modes. 1 over the square root of the number of longitudinal temporal modes. So yeah, for the stretch pulse, you have a lot of spikes, so the fluctuations will go down. If you imagine using dispersion, you essentially have a single spike mode, so the fluctuations will be very high, near 100% fluctuation. So yeah, it really depends on the E-beam going in, but it would be, in these cases it's SASE, so it'd be the usual SASE fluctuations based on the number of temporal modes.
Yeah, I have. Do you have any estimation on the fraction of particles get trapped in the density ramp?
The fraction of particles. So in principle, you will trap. Let me see if I can go to the picture. You will trap until you have sufficient charge that the beam itself starts to modify the Wakefield. So yeah, so you go down this ramp and you start trapping electrons and you collect charge. And eventually you collect enough charge, you start approaching the beam loading limit, and then you'll damp the wake and that'll turn off trapping. So, it depends on the specific parameters, but in general, you'll get trap charge approaching the beam loading limit. The limit where the trap charge starts modifying or driving a wake field of equal size to the laser-driven wake. So that's sort of in general. I mean, and then it depends on other conditions like laser evolution, the specific amount of trap charge.